Welcome everyone. Hi also from my part. I'm going to talk about the numerical methods for DFT and Beyond, and particularly on the grid-based operations like integration as a prime example, and also including some stories about the density update, which in our case, in the case of the FHI-aims, is rather similar operation. And I will also talk about, in the Beyond part, I will talk about the resolution of identity, which is needed to compute the exact exchange operator and the required force integrals there. During my presentation, I will also show a lot of scaling plots and show a lot of scaling results in the spirit of this tutorial. So you will see numbers actually that were done on supercomputer for the purpose of this presentation. So let's start. This is the first look one should have onto this when talking about scaling on large scale systems on large computers. One should first look at this kind of graphs. What we have here, I've chosen a test system. In my case, it's just the bulk silicon, so it's a periodic system. Then I set tight settings for that, just out of the AIMS playbook without any further optimization. And then I vary the size of the system in a unit cell. So obviously it's infinite, but in the 1 unit cell, I vary from 2 to 1024 atoms, which gives me an idea on the scalability of things. And in the spirit of the tutorial, I also list the platform here. So what I'm using here is a single node in a modern supercomputer with 128 CPU cores and 256 gigabytes per memory. And the build is done with the GNU tools or GCC and OpenMPI because they work better with the AMD platforms. So, but this is the first graph one should be interested in. So what we have here is the timings for each of the basic operations in one SCF cycle. When the number of atoms increases, goes from 2, where of course all the timings, if you have 128 MPI tasks and you have 2 atoms, all the numbers are here insignificant, obviously. Well, they are so small that it actually doesn't show up in the graph very well. But as you increase the size of the system, obviously you have different scaling behavior here. You have the total time here that seems to be growing more rapidly than some of the other operations. And the reason for the rapid growth, especially in the large scale systems, is the growth in the Kohn-Sham solution. So basically the solution of the eigenvalues and eigenvectors. This is something that Victor is going to talk about in the next talk, so I'm not going to be touching that. It's traditionally, it's been cubic scaling, and most of the algorithms still employ cubic scaling, but with a modest prefactor. So you see it only hits you around 1,000 atoms. Then we have the density update. Because this is a periodic system, we'll be using a density matrix because it's the only feasible option there. We have the Hartree potential solver, and then we have the integration that we will look into more detail in a while. As you see, all those operations, the grid-based density update and the grid-based integration, have much more favorable scaling than the Kohn-Sham solution. So basically, when you have a plot like this, you will eventually find out that it's for very large systems, it's the solution of the eigenvalues and eigenvectors which will eventually dominate. But of course, the question is, which one? Where is the point that it gets the largest? Which point in this system of increasing number of atoms? Where's the crossover point so that this becomes dominant? If you go even further in the larger system, it becomes even more and more dominant. I also wish to draw your attention to the fact that there are 2 values for the system of 250 atoms. And there is the first line that grows up to 250 atoms, and then there is a drop. And this, we will come back to this, why it is so, and we will explain it. But that actually is one of the points when you do large scale calculations. So we change a little bit of parameters here so that we are able to advance beyond 250 atoms without actually sacrificing any of the accuracy, but simply changing the algorithm to a more feasible one. So this is the first kind of scaling that one should know when one starts looking for large systems. and to see if, well, how large systems one can then afford, obviously. This is time for one SCF cycle, and to discount for the its periodic system, that the k-point sampling will always entail a constant factor. I'm using only a single k-point in all of these cases. Of course, it's feasible here, but obviously for very small systems, the numbers one would get out is not that feasible. Also in AIMS, if you want to do timing runs, you don't have to do the entire calculation. So typically the first SCF cycle, or the first or the second, is enough to get the timing for one SCF cycle, because they all repeat the operations. And in addition, unless you have force calculation coming up, which will then increase the time consumption for the step where the forces are calculated. These numbers don't include forces, so this is just a simple no forces, no stress tensors, because they're usually done only for one or two iterations in the SCF cycle, which can be expensive, but it's not really accountable necessary for this kind of scaling graphs. So the second graph we will be looking at is a double logarithmic plot. Here I have a different point of view on the problem. So I take a fixed size unit cell. I take 1,458 atoms. These are all multiples of the basic unit cell, and that's why that's how you get these numbers. And then I vary the number of MPI tasks. I start from 256 because it's the smallest one that can feasibly do this larger system, and then I go to a larger systems. And then I do a double logarithmic plot, and then I get the scaling with respect to the number of MPI tasks that I can use in the calculation. And this is something that the HPC centers will be asking for you. This is how you can sort of prove that you have a scalable code. The algorithm, then I just fit power law to these measurements or these timings. And as you see, the total timings have a pretty nice slope of minus 0.85. Minus 1 would be obviously optimal. And then the integration and all the grid-based routines actually scale even better up to the slope of minus 0.92. And then typically, if you have a large HPC center, they will give you a sort of a criteria to meet in order to be able to use the larger queues. Obviously, then when you get the right to use those larger queues, if you have such, most of them actually nowadays have some kind of a scaling requirement to prove the scalability of the application. Once you get the right to that, then of course you have to decide how many credits you want to spend, so how many MPI tasks you want to use to get to the solution faster. Because the more you spend, the more, well, then you have to apply more, and typically the queuing systems will penalize you for using a lot of CPU hours, and this means that the following jobs will start slower if there is queue. Okay, so these are the two plots I wanted to familiarize you with, so that you know what we are showing in the next steps. This is all, of course, purely measurements, so I haven't said a word what's behind all of that. And now let's get to see what's behind these integration operations here. As I said, about the Konsham solution that will be addressed in the next tutorial. So integration in density functional theory, especially in general, when you have a basis functions, we need to calculate the matrix elements that are composed of the base of the basis functions, and then you have some kind of a Hamiltonian, Konsham Hamiltonian that's defined on the same space, and you have to do such an integral. And same goes, you typically need, unless your basis functions are orthonormal, you need to also do the overlap integrals here. Basically, there isn't much difference. Well, of course, you have to evaluate different things here, but purely from an integration algorithm point of view, there isn't very much of a difference what you are integrating. The problem remains the same. I want to note that if you have, for instance, Gaussian basis functions, a lot of these things can be done with analytic formula. This is not the case in AIMS, so that's why we are not going to deal with that. we have to resort to something else. If you have plane wave basis functions, you can benefit a lot by doing fast Fourier transforms. Not everything goes by then, but a lot can be done by just Fourier transforming, operating, and transforming back. But as in our case, we have numerical atom-centered basis functions, or actually basis functions that don't necessarily have an analytic form. We need to do the, let's say, the classical or the basic integration, which just means we do numerical integration, and where the integration reduces into summation. Ups, there's a misprint. There should be just a summation, not the integral sign of here, of course. My apologies. So the idea is that the integration here reduces into summation over some grid points in the space, in the space we are considering, where we evaluate the integrand at each point, and then we put a weight on each of those grid points. And of course, as I said, the same thing goes here. So the integration algorithm is defined by taking the grid points, taking the weights, and doing the summation. That's pretty simple. It actually is, I mean, to do basic integration is actually pretty straightforward. Doing a quick integration and memory efficient integration is actually where most of the algorithmic stuff goes. As you probably know, in AIMS, we employ we employ atom-centered radial grids. This is the 2D representation of those. Of course, in reality, they are 3D grids, but it would look terrible. So we have an atom center, and then we have radial shells around this. So this picture is purely, it's not accurate. It's purely for the concept of the grid location, because I need to show a little bit how the grids then overlap and how things go. And then we have a grid point location, and then we assign a weight to it. And then in principle, once this is done, we can start evaluating all the integrands and doing the summation. But it's not that simple, as I said. So we have a lot of atoms. Typically, you want to do more than one atom. And that's sort of the point of the DFT, to do more than one atom. We have large overlapping grids. The grids can have a large extent. This means that they will overlap other atoms. They will, I mean, if you have a molecular system or surface or something, they will split in large into the vacuum. And what we need to do is we need to consider the integration points in batches. So we need to group them in batches. And when we go to the batches, we compute ready-made the matrices that will comprise the necessary integrands. So it is just split in two here. So I call them M and N. And then we sum up the local contribution for those batches. And when all batches are done, sum up. So how you do these batches then? Well, that is actually where the first integration algorithm comes in. There is a built-in batch division algorithm which just recursively splits the integration grid points into batches of roughly equal size. It's not exactly equal, but what you do, you start bisecting, and then you bisect everything you have here, and then you more and more split, and go on as far as you have a batch that corresponds to target size. There's a keyword for that, points in batch, but it doesn't really, I mean, the default value currently works well and has been working well for a pretty long time. I occasionally test if there has been changes, but so long, there has been no reason to change for the default. But in principle, you can change the target size of each of the batch, target number of grid points in each of the batches. And once you've done the integration, you just sum up things and be happy with the result or get the result. And this means that you have built up your matrix, which you can then feed into the eigenvalues solver, which is then the next topic. There are a couple of reasons why we do it like this. It's not, I mean, the algorithm has its found basis. And there are a couple of things why we do spatially localized batches, why we do batches of finite size, and why the batch size matches. First of all, when we do, notice that each of these are then spatially localized, and then you only need to evaluate one of the non-zero basis functions in each of the batches, which means that not all the basis functions are alive in one of those batch, which means that the number of basis functions you have here, phi j and phi I, are reduced. They are not all bases, but they are the local bases. That's the reason why we want to spatially localized batches. Then we want to use we want to use batches larger than 1 point. Obviously, you get the most localized batches if you have 1 point in each batch, but that's not sensible because we build up a matrix operation here, and we want it to be a matrix product, because then it's a BLAST3 operation, and BLAST3 operations are the fastest matrix linear algebra one can have. And this is where the speed of the integration comes in, not the scalability, but the actual execution speed comes from the matrix product here. And then nicely enough, when all batches are done, you can sum it up. And this is pretty easy to do in the MPI runs, because if you distribute each of the batches to each of the MPI tasks, in some manner, then you have to run only one MPI reduce, which is a fast parallel operation to collect all the values of the HIJs to the global matrix. We'll get back to this actually a little bit later, because it turns out this algorithm is sound, but the problem is that the size of these matrices can grow too large. The complexity. You have O endpoints, n here refers to any kind of system size, number of atoms, number of basis functions, or number of grid points, because all of them grow the same, roughly the same speed. If you add atoms, you get more basis functions and more grid points, and you basically, that's why we'll only use one scaling parameter n here throughout the talk. And then since the batches are localized, you have only one functions per batch. Of course, the number can be large, but it doesn't grow when the system grows, because you put the atoms somewhere far out. Their basis functions far out don't extend to here anymore, which means that in theory, we have, at least in theory, we have the ON scaling in the integration. And as we saw in the first slide, this is the case. So there is the theory and the facts actually go alongside with each other. So let's see then what this turns out if we look in more detail here. So this is the same settings as in the first slide. So, but let's have a more closer look at the integration operation here. So this is only time for the integration, the operation, the algorithm I showed in the previous slide. It turns out that when you fit in this bulk silicon tight settings case, in its ground state, it turns out that each atom in the integration costs you about, on this platform, about 0.087 seconds, and the overall intercept cost is 0.032 seconds. So this is the time that's spent in operations that don't scale by the atom. And as you see, it's pretty small. And also adding one atom doesn't cost very much in the integration. And this is the same, the scaling of the integration. It's just based on the operation, based on the fact that each of the MPI tasks deals with each of the batches. And this is also well parallelizable operation, which shows then that actually you get a decent parallel scalability for the integration and for the grid-based operation. What's actually surprising here, well, not surprising, but actually annoying here, that you have a 250 atom unit cell, you ran out of memory on this platform for the next unit cell. And the reason isn't actually the integration. The reason is the matrix storage. And the matrix storage means that when you store, when each of the MPI tasks stores the global matrix, when the system grows, the local matrix storage will grow larger and larger, and this complicates things for these settings. But there is a fix. So what you can do, you can switch on so-called local index by the keyword use local index, which switches on an algorithm which stores only the elements relevant to the MPI task doing the integration. So if you think again, a schematic picture. This there is the atom, and the basis functions of this atom are extending in this area. So you need to handle these basis functions only on these MPI tasks that are handling these batches, because they will never be needed here on the other batches. And then the algorithm goes the same way. You compute the local matrices, you sum up the local contribution, again, a vector operation. And when the all batches are done, you can just sum up. While it looks the same, it's a little bit more complicated. While you don't have a global matrix storage, you need to, first of all, you need to distribute the batches by location. So the MPI tasks each of the MPI tasks need to grab the localized batches there, or some kind of a blob around it, a spatially localized blob. This can lead to load imbalance, which you can then compensate by using load balancing with the keyword load balancing. And there is also the drawback that since now the summation algorithm, when the global matrix is not known by all the MPI tasks anymore, they have to communicate the local elements they have computed by a more complex algorithm than a simple MPI or reduce. And this means that some more exotic functionality may lack support. So you better consult the manual, but definitely there is a reason why you should at least try that. And here are actually the reasons. So what we see here is, again, the same benchmark, the bulk silicon. This is the graph we saw a moment ago. And as you remember, I ran out of memory here. But when I turn on the use local index, I end up here, which means that I can do much larger systems, much larger unit cells with the same system. And even the slope gets better. So the scaling or the cost of a single atom added gets better, which means that the use local index, despite its complexity, in this case is much better algorithm. And we can see also that the parallel scaling improves with local indexing because the slope gets better here. And actually even the absolute timing is better when you have 250 atoms in the unit cell. So it's safe to do this here. This is the basic algorithm. But if you run into trouble, or actually if you need more speed, you can try to use local index and see if it provides you. It gives you the same numbers. It's not about that. The only problem is that the handling of the matrices is different, and not necessarily all post-processing supports that handling. And what do I mean by that? In AIMS, there are two storage schemes. The first one, the original one, well, not the one, but the first useful one, is the global sparse matrix storage, where all the MPI tasks store the same matrix. And it's stored in a sparse storage format where you have the entries, row indices of the entries, and column pointers to row indices. So this is the compressed row storage or compressed column storage, depending a little bit, symmetric matrix, so it's actually the same. The problem is that the storage, while H is sparse, so you don't store the entire n by n matrix, that would be unfeasible, but it still grows with the growing system size. The good thing here is that you have a very simple and fast synchronization with all the MPI tasks doing their integration job over the batches with a simple OR reduce, and it's fast and simple. And that's why it actually was used for a lot of calculations. The other option is that the one that is used when you use the use local index is that the MPI tasks store only elements relevant to its batches. And this implies that you have a locally dense storage format, which means that you don't benefit the sparsity, but you have this kind of a local matrices that are dense, but that are only stored for those basis functions that are non-zero within those batches in that MPI task. The good part here is that if you add MPI tasks, your storage cost goes down, which means that your scalability improves, which means that your memory consumption goes down. which is actually for large systems that can be actually decisive factor, as we saw. I would have stopped at 250 atoms, which is not very good for bulk silicon from a per scalability point of view. Well, the price you pay is that you have to do a more complex synchronization of them, because now you have overlapping data here, and when you have to feed the entire matrix to the eigenvalue solver. The eigenvalue solver can't do partial matrices, which means that you have to sort of call to the right location and put them in the right location in the matrix, which is then stored in a, well, again, a little bit different format for the eigenvalue solver. But anyway, that's the two choices you have. Then a brief look. So that's how integration works in AIMS. Basically, as you've seen, it's scalable in parallel. It's order n operation. And another grid operation that's pretty close to it is the density update. So there are again two methods. I will talk only about one. Well, this is the first method. This is the textbook method, sort of. You can just sum up the single particle orbitals. So you end up with the density. That's the definition of, well, one definition of the density. And then you have the occupation factor there. Again, of course, if you have empty orbitals, they don't contribute. But the point is that you have a lot of these occupied orbitals too. So order n orbitals, order n grid points, order n squared if you calculate it directly from here. Not bad, but actually it's not order n, which is a little bit uncomfortable because grid operations would be more comfortable with order n operation. Well, we can write out. This is now the Kohn-Sham single particle orbital. These are the expansion coefficients or the eigenvectors, and these are the basis functions. And when you just insert this one here, I use the complex conjugate here, but assume real eigenfunctions, and you reorganize, you see that you have something that is actually dependent only on the basis functions. And this is, of course, order one for localized basis for each grid point you go in. When you go to a single grid point there, when a little bit the growing system size, the number of basis functions non-zero on that grid point will not grow because they don't extend all over the space. And then you have a density matrix here. Formally computing the density matrix is O n to the cube. But as we've seen from the benchmark, there are a couple of things that actually make this algorithm feasible over the traditional, over the orbital-based one, is that you have a very small prefactor. And in practice, the Dij is sparse. How sparse, again, depends on the system, but there's a lot of sparsity to be employed here, so that the actual update, density update, turns out to be order n for the practical systems one does, if you use the density matrix-based update. It's a default for periodic systems and optional for cluster systems. For very small clusters, I think the single particle orbital update is still fast. So, and here is actually the same graph where you see that actually switching on the use local index there even improves the parallel scalability there with the 250 atom units. And the slope is roughly the same if you look at here than in the integration. So basically the grid-based operations all run in the same algorithm. And the cost of the operation is based on the algorithm, not really on what you do with that algorithm. We have to compute the same thing. Okay, so this is the first part of my talk. This is the grid-based integration algorithms and the story of the use local index and the story of the load balancing too. The load balancing also on is these calculations because it actually makes sense to turn it on in most cases. But the other part of my talk was then about, well, not something completely different, but a little bit different. So of course, the story behind why we can't get away, because we were assuming that the Hamiltonian was very nice looking, and you have a local or semi-local potential that you can evaluate pointwise, and then you do the integration. And all that I showed is fine when you have this kind of option. So you add your local effective potential and no problem there. And if you accept that, then you can do band plots like this. This is LDA band plot, doesn't actually matter matter which local function it is tied with tied settings, and you have a gap of 0.466 EV, which is of course not that silicon bulk band gap. The problem is, of course, that the local functionals are not enough. You need something more. And traditionally, with the semiconductor business, you switch on to hybrid functionals, probably the HSC being the most popular one. I will use it as an example here, but obviously everything I say applies to all the functions that will use some kind of an exact exchange or screened exchange or derivatives of that. When you switch it on, you get a much more decent gap. The shapes you change also a little, but the largest changes are in the directions that the bands move here. By the way, all the input and output files are done with GIMS, which is actually quite nice tool, I have to say. I really found it for this talk because now the band plotting is finally easy, at least for me. Yeah. Okay, but what we have to do then? I mean, what we have to do to fix the well, it's called a band gap problem, but it's not really a band gap problem. It's a problem that you have a wrong electronic structure, which is a fundamental problem of explaining anything. So that's why to fix the problem, we have to go beyond local and semi-local approximations, and we need the exchange operator, which you can write down like this. And when you put it, these are now the all single particle orbitals. If you write it down in the basis, as in practice you have to do, you don't do the algorithm with the single particle orbitals, you do all the algorithm with the basis functions. You can write it like that. And there you have the famous full center integral, which shows you that, oh, this is no longer the local potential. So there is the things I showed previously doesn't actually, well, work here, at least not out of the box. And this is, of course, a very expensive operation to do. And it's a little bit, there has to be something, otherwise we won't be able to do any practical, well, we can do something, but it's very impractical. So, by the way, I will talk about the unscreened exchange operator here, but of course you can add the HSC screening here. It changes a little bit of things from the benchmark point of view. We'll see that, but for the theory, it actually doesn't change anything. You still have the 4 indices and the Coulomb potential or the Coulomb kernel. Oh, what people do then? People do something called the resolution of identity, also known as variational density fitting. So this is something that has been invented several times. The idea is that the pair products here, there are too many of those. So if the basis functions are complete, then you don't actually need to have a product of basis functions. That's sort of the, well, there are too many of those. So you should be able to expand these pair functions into a single index function space. And what people do, well, people just do that. They write one of the products here, or actually you can, of course, you can write the other one also the same way. You write the product like here, you expand it, and then you have these auxiliary functions here, and then you have the expansion coefficients. So that's the basic theory of what's called the resolution of identity, variational density fitting, but that's not the whole story of the algorithm. When you plug them in, you end up with an expression like that. So your 4 center integrals turns into a product of matrices, and it becomes 2 indices actually, mu and nu. And then the Coulomb matrix here is just the Coulomb interaction between the two of the or between the auxiliary basis functions. Now all it remains is to select the auxiliary basis functions, yeah, and define how to compute the coefficient Cij, because this is not really defining how you compute them. This is just a definition of what you would like to achieve with them, but it's not really how you do it. There is no metric, for instance, how to do the calculation. So let's see. Let's start from the how to compute them. Well, the obvious algorithm, again, is to minimize the error. So this is the error you have, and you want to minimize this. And there are 2 options immediately. You can either minimize the L2 norm, which is simple the norm of this, or you can minimize the Coulomb norm, where now you have this dash here means that you have the Coulomb potential there as the metric to do. When you do this, you end up with the definition, or you get definition. You get the coefficients C mu ij like this, whereas mu is the overlap integral of the auxiliary functions, and then you have to compute this kind of inner products, which again you can do by the integration algorithm, by the way. So this is basically integration over the grid, and this is what we call the RISVS, because it leads to an expression that looks like an SVS. On the other hand, if you use the Coulomb metric, you end up with an expression like this, where the inner product is the Coulomb inner product, and then here you have the Coulomb matrix, or the inverse of that, which is again defined as in the previous slide. And then when you write it, and this is what you call the RIV, and this is actually the method of choice that is employed, I think, more or less universally, because it's more accurate, and it also turns out to be very reliable, and you can make it efficient. The RIV is, you can actually use also RIV. I think you can still use RISVS2, but I'm not actually sure if anybody uses it for any purpose. And then you can write down the exchange matrix. You end up in an expression like this. This is the density matrix again here. And when you reorganize all the terms, I'm skipping a lot of points here, or some of the intermediate terms are missing, but you end up a symmetric formulation for here, and turns out that you actually need the square root of the Coulomb matrix there. Well, no problem, you can do that, but then you have a symmetric formulation. Please check the references and read through them. There are a lot of good text about this, and also reasoning how you should do that. The point is that you have to get rid of the false center integral, and you do that by the resolution of identity or variational density fitting, or whatever you want to call it, and you better do it in the Coulomb metric. Okay, that's already usable. Oh yeah, we have to select the auxiliary basis functions first. It turns out that this is actually maybe more straightforward. What you do in AIMS, of course, the previous one wasn't necessarily AIMS dependent, but this gets more AIMS dependent. What you do there, you form on-site productions of the radial functions. Then you have an option of adding radial functions to the construction of the auxiliary basis only. So not in the basis, not in the Conchamp basis, but only to add to the construction of these. And this you can do via for-aux keyword. We'll see about that in a moment. Then you have a lot of functions, far too many. You have to remove linear dependencies, but since this is on-site products, that's pretty fast actually. It's not a global operation to remove the linear dependencies. And then, as always, you add angular components with spherical harmonics to a certain order, depending on the orders you start here. There is actually a rule how to choose these. And then you end up with the atom-centered auxiliary basis. So the auxiliary basis in the radial direction looks like on-site productions of the radial basis functions, or enrichment of those that are added with the for-aux keyword. So basically, it's not that far away from what we are trying to approximate, which is quite comfortable. Okay. Everything okay? Well, not quite. It's a functional algorithm, so you can use it, you can turn it on, and you can see how it performs. However, when you start trying it further, there is a slight problem. Now, when you do an expansion like that, you remember in AIMS, all the basis functions are localized or are actually tied to atomic center. Now the expansion doesn't have no idea on the atomic centers. So if you well, it has, but they are the P's, the atomic center auxiliary bases, are defined on all the atoms. So basically, the expansion here takes two localized functions, phi I and phi j, their product, and spreads it all over the system. There is no way of telling that, well, at this point, until we tell it. But with the basic algorithm, there is no way of telling it that do not spread it far out, which makes the CIJ-mu then dense. But this can be fixed with no loss to the accuracy, but with a gain in the performance. We simply require that each of these pair products is expanded only by using functions that are generated on those particular atoms. So suppose you have there the atom I and atom J, and you have the phi i's living on this atom and phi j's living on this atom. So then in the expansion, you're allowed to use auxiliary basis functions from this atom and from this atom. But even if there is here as a K atom that actually has an auxiliary basis functions that is non-zero, where you would actually use it in expansion, you don't use it. You use only the ones on these two. And this is what is called the RILVL, or localized resolution of identity. And it turns out that the formulas look much the same, except now you have to reduce in the solution. You sort of solve in a much smaller subspace. You small in the subspace generated by these two atoms. And then and when you implement, when you can choose any of these methods, and you probably better consult the latest developments from the authors. But the current status is that the RI method, which you use, the keyword you use to select the method, is LVL defaults to LVL for Hartree-Fock and hybrid functionals, the ones that actually we started with. And if you go really beyond, then you use the RIV, but this for MP2, RP, and GW, for instance. But I'm not actually totally up to date. What is the latest word here? This is what's the manual word on things. Oh yeah, and then actually my favorite slide on the periodic RI. You know, while the formulas look confusing, but there are a couple of things that one should know in the periodic RI, because otherwise you get confused. In the previous slides, there wasn't really talk about the periodic one. But when you face the periodic systems, you have to make a couple of decisions depending here, because now you have really strong non-locality here because of the fault center integrals or the exchange operator. And in the periodic systems, we have block-like basis functions, of course. There's a new quantum number K from the first brilliant zone, which are then used to generate the generate the basis functions that are modulated by such a term, and then they are just switched to the next unit cell. And then you sum up all those, you get the one of your basis functions. Now there are two ways you can do this. You can stay in the reciprocal space and do the Fourier transform. It means that since you need the exchange operator at each K point, you write it out at each K point. This is now the fault center integral. So we haven't done the resolution of identity yet, but we will do it. We will do it simply by expanding by defining the expansion functions, the auxiliary basis, as Fourier transforms of the localized or similar block-like functions of the real space auxiliary functions. You put it in there, then you have an expansion coefficients that depend on K and Q, and when you plug in there, you get a well, again a summation over the K and the Q vectors over the first brilliant zone, where you have the Coulomb matrix and also the Cij. So formally looking the same. This gives you the reciprocal space RIV method. If you use RILVL, it turns out that this can be expressed as a sum. The expansion coefficients here can be expressed as a sum. So you basically have to compute only one set of those, because this refers to the central unit cell, and then you only need translates of that. But of course, you you have to only store one set of those, or one set of K vectors, instead of two set of K vectors here. But the matrix here is not sparse. It can't be. It's a Fourier transformation matrix. So basically, it just spreads the auxiliary bases again all over the space. This is still used for periodic GW, but it's not used for periodic resolution of identity in the hybrid functionals or Hartree-Fock. What you do, you take another route, and I know this sounds adventurous, but what you do, you define the exchange matrix as a Fourier transform of the real space matrix. Then you just write out the real space matrix. You in here you use the same resolution of identity as previously, and you end up, but now just counting for all the periodic images in the system, because now you have to look also for the neighbors that are in the unit cells beyond your central unit cell. And you end up with an expression like this for the RIV. RILV again drops a lot of terms, but not all of them, because you have periodic images of the atoms, you have to account for those. But you get away by using the RLVL, using this very strong screening of small elements. It's possible here because now you have the real space screening property, which is lost in the reciprocal space. You get the sparsity of the Xij, and then you actually turns out that you have to make the V mu V, also the Coulomb matrix also born from Kalman periodic. It's all in Sergei's paper. It's a little bit long story, but the point is here that it's beneficial to do the RI for the periodic systems in the real space because you get rid of so many elements. Okay. Let's see. Performance and scalability, HSE06. So this is the testing then. What we have here is the complementary error function as the screening parameter. And on the left-hand side, I first test that is there a k-point dependence. There shouldn't be a major one because it's done in the real space. And as you see, there is actually that much, there's no problem in that. And we also have a decent parallel scalability, which means that these computations are, you can put larger and larger system, or you can take a larger and larger computer, more and more CPUs, and you can plug them in, you get a decent sloping here. And these are all with 2.2.2 K-grid. So actually it gives me real eigenvectors there. And when you do the Fockmanship, then when you do check the other way around, when you check for the time for the Fock matrix construction, you end up with a very decent linear scaling there, but with a much larger slope than you had in the integration. So there is a lot of more cost, but the scalability isn't that bad. But obviously, at some point, even the slope is going to kill you. And there is also added initialization cost, which is roughly the same ballpark. You have to do this, of course, only once per the SCF cycle. This you have to do in each iteration. So this is for a single iteration. But for comparison purposes, the numbers on the previous slide were used in tight settings, as I was doing for the integration. So the numbers are there comparable. All the systems have been comparable so far. But if you want to do the hybrid functional calculations, you should also definitely check out the intermediate settings, because they are often sufficient and there are savings available. So this is the tight setting line, and this is the intermediate setting line. And as you see, even for the 128 atom system, there is a major difference, and the slope gets down by a factor of, well, 2.5. And the difference isn't that much. So if you look for the silicon tight, there are two basis functions in hydro, 1D and 1G. In the intermediate one, you comment out the D and you put the G into the auxiliary basis. So the G is no longer in the Kohn-Sham basis. And this alone gives you a reduction of the execution time, which is quite considerable. By the way, here is also when I said that when we do the screening one, here you see how the real space screening actually has an effect. If I remove the screening and do the half-tree Fock with exactly the same geometry, so the spatial localization is the same, it turns out that with intermediate settings, you have to use something like 425 seconds. So the HSE screening factor here drops so many elements that you get even lower, that you save almost half of the time compared to half-tree Fock. Obviously, if you have to do half-tree Fock, then it's again the system you have to first choose the right model. I agree, but this shows you how the real space screening helps you, because it's more and more aggressive in the HSE. Okay, I'm almost done. I think all my time is almost out also. So a couple of words still, because this relates to the scaling and scalability. So you can also do with AIMS, with the operation I've shown before, especially the integration. You can also do GPU computing. which means that certain operations can be offloaded to GPUs. As you know, more and more supercomputers are going to be more and more GPU computers, and this means that at some point you have to do some GPU computing, which means that it's good that you have algorithms that work on GPUs. The general rules is that you should use algorithms that are vectorizable, have no branching statements, and have a minimal communication between CPU and GPU. What we do in AIMS, let's get back to the integration algorithm, for instance. The RIA, resolution identity algorithm, is not yet on GPUs. What we do on CPU, we compute the matrices. The reason for using this CPU on this matrix is that there are a lot of ifs, because you have to select out those basis functions that you actually are non-zero on the batching question. So you have to use a lot of conditional statements there, which doesn't lend itself very well to GPUs. Then you copy the data to GPU. You sum up the local contribution on GPU. Well, GPU is very good, which is basically doing the matrix product here. Again, it turns out that this works best with local dense storage. You can check Ville Havu's paper on that. Why is so? Which means that use local index is actually the best option for GPUs. And when all the batches are done, you just copy the data back to CPU, and then the CPU feeds it to the eigenvalue solver, and the story goes on. Again, these are not my numbers. These are from Ville's paper. So what you see there is that, again, silicon bulk, tight settings, surprisingly same settings, and a single K point. But the timing is here for the full calculation, including forces and stress tensor. And the trick is here that this is CPU only. This is when you add the GPUs, and here you see the systems. You add about 1, 4, or 4, depending a little bit on the system. And it turns out that you can get a considerable speed up by throwing in the GPUs if you have those. So the integration algorithm goes happily here. Well, actually, that's the total time to the solution, but the integration is dominant here. And the forces and stress tensor. How to get it? Again, it's in the manual. You have to build a GPU-enabled binary and then set use GPU true. And then you can run a GPU calculation if you have a GPU-based HPC machine, as most of us will at some point have. Okay, I'll conclude first. So first we talk about grid-based operations. We show that there is an order and scaling with a modest prefactor. And from the user point of view, the point is that use local index when possible, when it doesn't bother you, and load balancing when needed. I mean, if you get a large imbalance, you can try with load balancing to see if there is an improvement there. And GPU support is available. You can experiment with points in batch, because now the batch size has some effect on how the GPU works. And on the other part of my talk, I talk about the resolution of identity operations. It turns out that they are also order and scaling, but there is a much larger prefactor and cost of initialization. You can use the default method, which is RIV or RILVL, or you can select with RI method, but then actually you have to know what you're doing. The accuracy can be sacrificed. It's important, especially for hybrid functionals and Hartree-Fock, to test the intermediate settings. The values can be pretty much okay, and you can save a lot of effort there. And if you want to tune your own basis, you can experiment the 4 AUX, because then you add stuff only to the auxiliary basis, which is much cheaper than adding it to the entire basis, which means that you improve the accuracy of the resolution of identity. Okay, thank you very much for your attention, and sorry, Sebastian, for overdoing a couple of minutes.
No problem. Thank you so much. Can you hear me?
Yep.
Oh, perfect. Yes, thank you so much for this very clear talk about not so trivial problems. And I wish I had this lecture when starting with FHI-aims, but it was a real nice introduction. Thank you so much. We have one question already in the chat by Levi Keller. Do you want to ask yourself, Levi?
Yeah, my question was regarding in the integration part you were talking about bisection. So I was just wondering if do you always have to the end segments.
Yeah, in the algorithm I showed. In practice, you don't, because there are a couple of additional tricks we have, because it turns out that you can't do a global partitioning of the grid points, because then you would have to store the coordinates of all the grid points somewhere, and you would run out of memory. So what we do here, the thing, you get 2 to the, no, actually you don't get 2 to the power n batches either, but there are 2 ways of doing that. If you have only a single MPI task and you do the batching, then basically you split, but you can stop the splitting on each of the subtrees when you meet the required size. Which means that basically when each of the operations splits one of the batches, but it doesn't mean that they all go deep enough, they all go equally deep, which means that one leaf can be much shorter and the other one can be deeper, which means that there are not necessarily 2 to the power n batches, even if you do it with a single MPI task. If you do it with multiple MPI tasks, as the default is, you actually first, you split the grid by hashing to a bins, which are then dealt with separate MPI tasks without knowing from each other. This is an additional complication. Otherwise, you run out of memory because you can't store the grid points anywhere. It's a confusing problem because you have to operate with grid without actually being able to compute all the points on it. Yeah, but even in that case, there aren't 2 n batches because you split each of the sub batches as long as you get the target size. And since the grid point density is not even, some of the bisections can stop earlier. That wasn't very clear in my presentation. Can stop earlier than others.
Okay. Cool. Thank you.
I think you can say there's even number of batches there should be, unless you get away with 1, because you always split them. But that's, yeah, fair question. True.
There's a question by Daniela.
Yes. Hi. So very nice talk. Very timely for us as well, because we are very fresh of submitting a proposal to the Swiss supercomputing with FHI-aims. And of course, to submit the proposal, we had to perform some tests. And since the nodes for which you can submit the large users projects are GPU nodes, or at least they are hybrid nodes, you have to prove that the GPU usage is so that the GPU is exploited by the code. And after a bit of help also from the forum, we could produce a code using GPU and use GPU, everything okay. And we got also very nice speed up on the PDE tests, on the GGA test with acceleration due to GPU with the same number of nodes, but also a good scaling. The bad things comes, of course, when we try hybrid, and when we try hybrid, then we try to see if we have some GPU acceleration or usage there. And Volker Brum has already told me that okay, there is still much to do, and of course there is this paper by Volker 2020, computer physics communication. We are reading that, and I wonder if there is some hint that you can give about the hybrid and GPU.
Unfortunately, nothing very detailed. I mean, the general rules, if you really are going to develop on that, it's definitely, of course, one would say it's doable because GPU, but the point is that you have to figure out how to use a storage scheme where you don't have branching statements or non-contiguous access. I haven't checked the current storage scheme for the hybrid functionals, basically it boils down to the full center integrals, because that actually has been rewritten a while ago, and now it works for the CPU much better. But if you can find matrices that you can push to the GPUs and operate there, then you should be able to gain at least for that operation. But Volker, do you have an insight on that? Because
I have some comments, because as Daniela said, this is future work as far as the GPU goes. But if you look in today's GitLab, FHI-aims GitLab, and see what was committed about a few minutes ago by Florian Merz, who's been working in general on the hybrids, this is actually one of the ongoing CPU optimizations. And so that's a strategic choice we made because we're well aware of the GPU functionality. Florian has been pushing on the CPU optimization because he's working on issues such as load balancing and also especially for very many available CPU cores, right? And so this is a restructuring of how the operations are split up in the hybrid functionals that makes things faster. And so Florian's point is that this work is actually the preparatory work that you need for the GPUs, or at least he made that point about a half a year ago. And so that's why we went that route.
I mean, if you look at the equations, I mean, basically, there's linear algebra, right?
Yes.
So it should, if you look at the, I mean, if you look at these equations, but the point is that if this Cij mu is sparse, you would have to make it somehow dense in order to run on the GPU, as already Will showed, that all the magic operations you have to have. No.
Yes. And so actually the linear algebra at the heart of the hybrid functionals, once you've reduced everything down, is still dense. Right? And so this means it can actually be GPUified. It's just a question of the workload distribution. And so there is some hope there, right? I'm hoping that this will be coming, but it's a matter of getting the hybrid functionals into the infrastructure that needs to be there.
So let me ask maybe a provocative question. Suppose that in the future we have a new machine that has a partition with very powerful CPU nodes, multi-cores, and also a partition with multi-GPU or something like that nodes. So is the advice here that we try to get the best results on the CPU multi-core nodes and like access there is more viable with respect to waiting for the development on the GPU?
For hybrids for now, so if the question is now, for hybrids, getting more power out of the CPUs is advisable, because that should translate directly to the code that is there. Right? Now, there is a small issue, but that's on the cusp of being relevant, and only if you do very large systems. So at some point, the hybrid functionals actually start costing less than the eigenvalue solver. And that's a very interesting observation. We didn't have that until recently, but it turns out that at this point, you can push the hybrids to sizes where it's actually the eigenvalue solver that dominates again.
And then again, and then
at that point, even with the current code, it's a good question where you're at in terms of system size, right? So if the CPUs are good enough in the GPU nodes, and the eigensolver dominates, then it might be a trade-off, but it requires more benchmarking, I guess.
That is what we are going to do in the next months. We will keep you informed and ask for help. Thank you.
I'd be very interested, right? My thinking is that for the hybrids, something has to be doable reasonably efficiently with GPUs, because it's dense linear algebra, as Ville pointed out, at the heart.
And also, I forgot to mention, but the current AIMS implementation runs only on NVIDIA GPUs. And if you are considering future computers, there's going to be AMD GPUs. And of course, the vendors always say this is not a problem, but I never trust the vendors in this respect. I've seen that too many times. So to my knowledge, we don't have AMD GPU benchmark data. If anybody knows better, I would be very glad to know.
I think there's somebody who's under non-disclosure agreement somewhere, but I don't know.
We would have a testing platform, now, because there is.
Thank you very much for the extensive answers. Thank you.
Another question by Dimitri.
Yes, quick question regarding two things. First of one is RI method.
Yep.
So imagine that I'm using PV0. Will the RI approximation be switched on automatically, or should I take care of this with the keyword? And what would be the default value for that?
PB0 is Hartree-Fock based, So basically you use the LVL, and I think it should default to that.
So I do not need to take care of this, or shall I explicitly provide this keyword? This is my...
No. I mean, the aims defaults are nowadays pretty reasonable for most of the calculations. So the less you put in the control in, the usually better you are off.
Good to know. And then, we also recently discovered that there is an intermediate basis set appeared in FHI-aims, and we thought before we only use tight and light in our daily base calculations. And from your talk, I realized that it's 5 times faster, as far as I can see.
Well, in this example, your mileage may vary, but it's definitely worth testing if you are doing. I mean,
but you barely mentioned that you might get acceptable accuracy. Or what did you imply with that? Acceptable.
Well, I'm a little bit conservative because I don't want to say you get the same results. You will not get the same numbers. But for instance, I'm from the semiconductor background. For any publishable semiconductor result, a reasonable result, for instance, think about formation energies, band gaps, things like that, you get away with intermediate. But then there can be fields where you need more accuracy. So from my point of view, I'm happy with intermediate, and the tight is rarely needed. Light is too little, that's we know.
That is clear. So because we are playing some tricks with intermediate and tight basis set, good that we have intermediate, so with light and tight basis set, and good that we have right now an option with intermediate basis set. Then the last question is regarding this RI approximation. So you mentioned something about additional thing which we can play around with the basis set. I kind of did not get it. So does it mean that we need explicitly modify basis set, or will the basis set be selected behind our back with auxiliary basis set? This one.
Yeah. Well, the input defines the auxiliary basis set by forming all the products and also adding the 4 aux functions. My point was only that if you really want to do very large systems, it may be worth doing your own basis set, which is not light, tight, or intermediate, but is just for the target quantity you are looking for. It's a lot of effort, but it's been done just for those reasons where you want to have a certain accuracy on a certain target quantity, but it's a lot of testing. And well, my point is only that you can do it. And if you're really in a point where intermediate is not working for you, tight is not working for you, you can try adding some of the functions.
Basically, it's like an experimental thing in which you need to put a bit more efforts in order to get the acceptable performance and accuracy.
And you definitely need a smaller system to test with. So don't test with the largest system, but use a small test system like, well, again, in bulk systems, it's easy. Use a small unit cell and see how much the energies change. And then this is usually extrapolated to a larger unit cells. Also.
And that is clear. Good. So it's somehow not a standard thing which you should immediately go for in FHI-aims, rather an experimental one, which is requires additional testings.
Again, in the history, there has been a lot of playing around with the basis function sets. It's not that necessary anymore, but we've been playing around with with the radiuses that they extend to get just the right numbers. But I don't know. I would first say that try these presets and then modify them if you want to increase your accuracy or lower if you have to lower the computational cost.
Fair enough. Good to know. Thanks.
There's a raised hand by Volker. I think he will have some comments on that.
Yeah, I just wanted to comment on exactly your questions, Dmitry. So first, the intermediate sets seem to be pretty globally usable for semi-local and hybrid DFT. So we've been doing essentially the entire hybrid functional work in our group based on intermediate basis sets, and so that's also how they were tested, and they appear to work. The history of the tight basis sets, especially for the molecular case, is that if you want to do something like a weakly bonded, hydrogen bonded system, then you get more accuracy, of course, by taking more basis functions. So you can use tight to check. And so that's why we always had tight. But especially for hybrid functionals, if you're dealing with hybrid functionals, the cost of hybrid functionals goes up so dramatically for relatively little gain that the
It is.
intermediate settings are the first thing to do, I think, across the board. That's our experience.
Thank
The
you.
second thing is the for aux keywords, you also don't need to do much with them in my experience for semi-local and hybrid DFT, but they did show up as a part of the last tutorial. So if you do GW or the random phase approximation, then in some cases you can actually gain some accuracy by increasing the auxiliary basis set, which essentially expands the Coulomb operator. And so that was discussed last time. So for the hybrid functionals, there's actually multiple examples of this in the paper, the 2015 paper by Arvid Erik, that tries to explain this concept that is embedded in these for aux basis functions. And you see that you don't gain terribly much. In fact, every one of our tight species defaults also has one for aux basis function in there that you can just comment in to check, and that goes back to Arvid's paper. That's explained there. And then if you go beyond hybrid, so if you really have to do sums over states with an explicit Coulomb operator, then you can gain a little bit. But again, that was also explained in the last tutorial. So that's hopefully more transparent.
Thank you.
There.
Okay, I think I have to close the discussion, and I'd like to thank Ville again. So